So today I will talk about the thin film stress measurement, especially at NUFAB. Before we really start, I want to do a quick survey. See how many of you ever consider film stress, either in film deposition process or in device fabrication or even in film characterization. So if you can put yes or no in the chat, I just want to get some idea. Yeah, we have 5 response. 4 say yes, and okay, 5 say yes. All right. It's pretty good number for the audience today. Yeah, so film stress is actually a pretty important parameter for films, but in many cases, and especially among the new students, is often ignored, and that's why we want to revisit this topic today. And I will show you how to do the measurement, also the background behind it. All right, so here's an outline. So first we'll talk about where does the film stress come from, and then so why should you care about it? So natural question is how to measure it, and then I will show the film stress measurement system at NUFAB. Then the last is how to control the stress. So where does it come from? So quick answer is it's induced during the film deposition. So there are 2 categories, one intrinsic, one is extrinsic. So intrinsic is mostly it happened during the deposition. So it's related with the non-equilibrium nature of the deposition. For example, if we talk about CVD, a chemical vapor deposition process, so there's atoms arrive at the substrate that's accumulates and grow the film. So the first deposit atoms may not occupy the position of the lowest energy. So but because of the high deposition rate or very low atom surface mobility, so the first atoms may be trapped by the next newly arriving atoms, and that is results the intrinsic stress. So common causes can be the lattice mismatch between the film material and the substrate, and also impurities either in the films or in the substrate. And also related with particular coating growth process. Extrinsic stress is related with the environment change after the deposition. So because during depositions, usually in a vacuum chamber, also in elevated temperatures, and the environment will change after the sample is removed from the chamber. So common one is thermal stress. So we'll talk about this thermal stress in details in the next slides. And another common one is related with non-uniform deformation at the film and the substrate. So, okay, we will so thermal stress, why I talk to this one specifically, because this is the most Euro type of extrinsic stress and is well understood. Thermal stress is related with thermal definitely. So it has a temperature change and also the thermal coefficient, thermal expansion coefficient. So this demonstrated in this picture. So we have this part as deposition temperature and this part is room temperature. So during the deposition, so there's no thermal stress and the film grown on the substrate, and the film thickness is much smaller than the substrate thickness. And these 2 materials have different thermal coefficient alpha F and alpha S. But once it's moved to the room temperature, usually it's a cool down position, and both material will shrink. And this shrinkage is totally defined by the thermal coefficient. So if the film shrink more than the substrate, then it will have this kind of structure. So its edge curves up, and this is a tensile state. And if the substrate shrinks more, and the edge of the substrate will curve down, and this is a compressive state. Examples for those kind of two states is like if you deposit polyimide on silicon, you will have a tensile, and if you deposit silicon oxide on silicon, it's going to be a compressive state. So this is totally defined by the thermal coefficient of the film and the substrate. It's a okay. This is so what's the consequence if you have a lot of stress? So you talk about these two cases. One is compressive and one is tensile. And then we have two more splits. So one is if you have a good adhesion, the film is very strong. The adhesion is not very good. So the film is not very strong bonded to the substrate. For the tensile case, the film can crack. And for the compressive case, the film can buckle and delaminate. So this is extreme case, and it will definitely break down your film on your device. But if the adhesion is very good, and then you have to, so the force will be applied into the film because film is much thinner. So it will break the periodic lattice structure and make the plastic deformation in the film, or even have some micro cracking. And some cases it has a viscous flow, and you can result in a non-uniform deposition. So this is none of those cases you want to happen. That's why you should care about the film stress. Okay, so the way is that first you need to know how to measure the stress, and then you can consider about it next. So measuring the stress is like measuring any other physical parameters. There's a lot of methods, but today we talk about the conventional way. So conventional way doesn't mean it's bad. Usually it's not so advanced, but it's simple and easy and fast and also reliable. So the conventional technique is called deflection technique. So I show the diagram here. So it's based on assumption that the stressed thin film will bend a moderate thick substrate by a measurable degree. So this is a film with substrate and it's bend a little. So now we have a laser. So we have two lasers actually, but a laser come to a mirror, and the mirror will reflect this laser, so it will shine vertically onto the sample. Because the sample is curved, so the reflection will not go directly back, so it will go away to a detector. And this detector will measure the distance between the reflected light and the instant light. So this is a delta. And it will use a delta to calculate the film stress. So the calculation is here. So this is a curve, the measured raw curve. Okay, I forgot one thing. So delta, yes, the measured delta. But meanwhile, this laser will scan across this film. And so we have two parameters. So one is control parameter of the scan length, and one is measured parameter of this delta. Then eventually we'll have a curve of the delta as a function of the scan length. So this is a sample lateral length, and this is a delta. And so this curve can be fitted by a parabolic function. So in this fitting, you will have three parameters, A, B, and C. And this C will be used to calculate the radius of the film of the sample. So radius is showing up here. So it's curve, it's assumed it has a radius as R. And this radius equals to 1/2c, and then you can use this radius to calculate the stress with this Stoney equation. So in this equation, the first part is the material parameters of the substrate. So this is just some constant parameters you can easily find. And this part is the thickness. TS is the thickness of the substrate. TF is thickness of the film. This part is the radius part. RA is radius before film deposition. RB is radius after deposition. So this equation also indicates that there should be 4 parameters measured both before and after the coating. So before the deposition, you should measure the thickness of the substrate, the TS, and you measure the radius RA. And after deposition, you should measure the thickness of the film and the RB. And you put them together, then you can calculate the stress. So our system at NUFAB is called Tahoe FLX 2320S system. Is very popular laser film stress measurement system. So what it does is it automatically scans the laser across the film and plot the data and automatically calculate the stress. So this is a typical data output by this system. So it has this mirror distance and diffraction, and also it calculates stress directly displayed here. So I want to go to a little bit features of this system. So first, it has 2 lasers, 670 nanometer and 785 nanometer. The reason for these 2 lasers is because during the measurement, the reflection is very important. If you don't get a reflection, you can't do the measurement. So with these 2 lasers, you can get a reasonable good reflection with a large variety of samples. Then the measurement range for the stress is 1 megapascal to 4 gigapascal. It's pretty big range, and accuracy is pretty good. Is only 2.5%, and scan range is programmable up to 8-inch. So which means you can measure a film up to 8-inch in diameter. Minimum scan step is 20 micrometers, so it can get very dense data. And we also have the function for 3D mapping and also in-situ stress measurement. So I will talk about this in-situ stress measurement with the temperature with temperature later. Again, as any other equipment, all the equipment has its limitations. So first limitation comes with this technique actually. So it measures the overall stress. It doesn't measure the local stress. Although it has 3D mapping, but it's generally a big area stress. So if you want to measure local stress, so this is not a technique you want to look at, and you should think about something more micro structure like X-ray, Raman, or infrared spectroscopy. So those can measure the local stress. And there are also some micro machines, gauges, so those kind of things. So, the second is actually the second and third is also related with the reflection. So important thing is that we should get a good reflection. But if your film is so rough and it's going to be very low reflection, and you can't measure it. But if your the film is smooth, but for some reason those 2 lasers cannot get a good reflection, it's kind of transparent. So you will consider not using this optical method. Instead, you can use some physical method like our profilometer DECTEC. So it also has a function to measure the stress, but relatively is much slower and not as accurate as this system. Okay, so this is measurement, and so I'll show you quickly about the 3D mapping. So this is 3D map we measured at NUFAB, and this is aluminum oxide film grown by ALD at NUFAB also. So reason for measuring 3D is because you have a 2D film, so why you want to have 1D measure? So 2D is that so measuring a two-dimensional is definitely a better characterization than measuring in one-dimensional. Okay, so the last thing is because you know how it comes and how to measure. This next thing is how you control it. So again, the control is means you control the film deposition. So and there's a lot of parameters during the film deposition. And there's many can be controllable. For example, the film thickness and deposition temperature, deposition rate, also the choice of substrate. So all those can contribute to the stress, and you may not know exactly which one is the most important one, but you can start to tune it, and you can pick any parameter and try to adjust it, and then you measure stress as like this picture. So films, it measures the stress as a function of the film thickness. So just like measure, grow, measure, and adjust parameter, and measure again, then you can get a good picture of how to control the process parameter and eventually adjust the film stress. But if you say you don't want to change the deposition parameters, or you don't want, you cannot change it, whatever reason. So you can do the thermal relaxation after the film is grown. Thermal relaxation is actually annealing. So annealing means a slow thermal cycle. You heat up slowly and stay at a temperature for a while and then cool down slowly. So this can usually reduce the film stress quite a lot. And here's a picture showing up, so measured by the system, by our system too. So as a function of temperature and how the stress was released. So first heating up and then cooling down, it can reduce the stress quite a lot. So you can talk a little bit deeper about why it can release stress, because annealing and at a heated temperature, so it heals the lattice structure. So and the film can be crystallized. And when the stress is there and the film is trying to crystallize, and something called crystalline slip will happen. And this is how it looks like. So it's kind of like crystal, but it kind of slip a little bit at different in a certain plane. So this process can strongly reduce the stress. For our system, we have this in-situ stress measurement with the temperature. So that means you can do the annealing process at the same time you measure stress. So this is a quick way to reduce the film stress after the film is deposited. Okay, so that's everything I want to show. So anytime, so it's time for questions. So I didn't see anything in the chat yet, but you can just unmute yourself and ask question.
Hi Ying, this is Dieter. I had a question for the two lasers. Are you using them at the same time, or is it like if one wavelength doesn't work, you just switch over and try the other wavelength? So are you using the two lasers at the same time, or is it exclusively that you use one or the other and you just try which one works best?
So usually this 670 works for a lot of material already. And if it doesn't, so first is it use only one laser to measure. And usually we pick the 670 because it was for a lot of material. And if it doesn't work, you can select this one. And this system can also automatically select. So before the measurement, it will look at the film and find which wavelengths get the best reflection. It will automatically select that one. So you can kind of like don't need to worry about it. It will pop out. It will use the best laser, and it's use only that one.
Oh, I see. Thank you. So the most general one is the 670. And
Yeah.
if there is a problem with that, there's the option and the system will tell you to go to the other laser beam.
That's right.
Oh, okay. Thanks.
Hi, Ian. This is Xiaobing here.
Mhm.
So I have one question for this stress measurement. How can I say? What is the spatial resolution? For example, how large or how?
So it's the minimum scan step is 20 micrometer. So so I would say this 20 micrometer in the lateral direction, and to the size. So we recommend size is 4-inch or 6-inch wafer, but this system can handle any size up to 8-inch.
How about the spatial resolution in the thickness direction?
Oh,
Not,
no, it's it doesn't
surface.
matter that. No, it's only the surface. So you have it cannot look into the film. No.
Then you mean that in your NUFAB there is no equipment to measure internal because
No.
no way to measure internal.
Yeah, this is not a local. It doesn't look at the microstructure and see locally how this much stress. It's general after deposition and what's the overall stress.
Okay,
Yeah.
and how accurate it is? For example, 5%, 10%. I mean, how accurate for this measurement?
So I have the accuracy here. So it's either whichever
2.9.
largest 1 megapascal or 2.5%. So if you have 4 gigapascal, so 2.5% is 10 megapascal. Yeah.
Okay.
Like
So
that.
yeah, I'm sorry. I mean, I have another question. So another one is, it looks like the principle for this measurement is depending on the roughness of the film. For example, if during the deposition process, for example, I mean, if it is for example, if there is no stress, but there is still the roughness is very large, then I mean, can this one still measure?
So it's as long as you can get a reasonable good reflection. So to me, to my experience at NUFAB, the roughness of the film can go up to 10 nanometer. And we don't have, so for this range, we never have problem with this system. It's still considered pretty reflective, but some user can come like with a film like spin coated film by nanoparticles, and those kind of particle can be big size, can be very rough, and this could be a problem.
Okay.
So it really depending on how rough. Generally rough, less than 10 nanometer is fine.
Okay, I see. Thank you.
Okay, so I have a question in the chat. So is there a way to add certain parameter like electrical potential or temperature? Add you mean add the parameter to the system or add the parameter to the film?
Yeah, I can clarify.
Okay.
So is it possible to bring like a potential stat and like hook up, like 2 electric leads to like the ends? Like can we kind of leave the door a little bit open of the instrument, or is it not possible?
So the door keep locked because of the laser safety. It's a
Okay.
class 3 laser, but it's pretty big chamber inside. And you can see this is our PC and this is the chamber. So an example, for example, is 4-inch. You have pretty other, space to accommodate in something else. You don't have to leave the door open, but we don't want you to leave the door open, but as long as you can fit it in, so we have no problem. And I hope you don't heat it up when you have some extra part inside.
Cool. Thank you.
Okay. All right. So did you implant also cooling? Oh, we don't have cooling for this one. I know the system can have the option of the liquid nitrogen cooling, but this one we only go to room temperature. Okay.
Hi, Ying.
Yep.
This is Ray from UW Medicine. Very nice talk. I have 2 questions. The first one is, can you measure some semi-transparent substrates? Or in other words, what is the reflect index limit of your measurement? The second question is, you mentioned some techniques people use for measuring local stress. Could you remind me again, what are those techniques?
Okay, how about I send you some reference about the local stress. So there's quite some actually, mostly using X-ray, Raman, or infrared, using those diffraction techniques or the spectroscopy. So I can email you some reference later.
Okay, I will contact you with email. Thank you.
Okay. Wait, what's okay, so semi-transparent substrate. Well, so silicon oxides and silicon nitride and the glass, they're pretty transparent. It's still measurable.
Okay, good.
Yeah, so it really depends on what material. As long as you can have reasonable reflection, so we use silicon oxide substrate, so no problem.
Okay, thank you.
Okay, thank you for coming, and you can always email me on NUFAB. So this is my email address and it's NUFAB. So pretty easy to remember. Any question, just send the email over and I will answer it. All right.
All right. Thank you very much, everybody.
Thank you.